With that, I'll hand it over to Team 2 to kick things off. So John Carter, Adibola, when you share your screens, and we'll get going.
All right. Yeah, thank you, Ryan. Yeah, thank you for coming to our presentation. We are Team 2. Yeah, we've learned a lot these past 8 weeks, and we're very excited to share some of that. But there we go. Yeah, I'm Carter. My teammates will introduce themselves.
Hello, my name is Adebola Babatunde Lawal, and I'm from Howard University.
I'm John Cates. I go to CU Boulder.
I go to UW-Madison. I forgot to mention that. But anyways, here's our table of contents. Yeah, we're very excited about this presentation. Now I'm going to hand it off to Adibola to talk about our market research.
So our market focus of our research was incorporating the CAN bus system into the semi-truck market. We wanted to use vehicle telematics to increase safety on trailers and semi-trucks, with ideas ranging from weight sensors on the axles to a collision notification system that would tell the driver if a collision had occurred. We eventually narrowed it down to CAN sensors on the trailer doors that relay a message if the doors aren't properly locked when the drivers are in motion. A need exists amongst commercial trucking companies that might be interested in including CAN in their electric and non-electric semi-trucks designed for their major customers. And with that, we go to the next slide.
All right. Yeah, so comparative analysis. Yeah. What makes our product unique? Well, as you might know, there are a lot of different trailer sensors available on the market, both from third parties on the aftermarket and from manufacturers. Most of these are cameras that monitor the inside or back of a trailer. And for the most part, these require the driver or someone else to actively monitor the video feed to know if something is wrong. So if a door opens on the trailer while it's driving, the driver might not notice for quite a while. Because you can't constantly monitor the screen while they're driving. So that's where our product would come in. It'd be integrated into the truck. It would notify the driver through the dashboard, maybe play a noise, so they'd know right away when the trailer door is open. Yeah, sound could play, warning would show. It'd also be recorded possibly in a data log that could record the time and where through GPS. Yeah, so the most similar for competition, the most similar existing product, the biggest potential competitor we could find in our research was this aftermarket product. I got a picture of it here, Trailer X, or sorry, made by Truck X. Their product, it's a door sensor that you install on a trailer door, and you pay an annual fee to receive data on your phone to know when and where a trailer door opens. The advantage of our trailer or of our product is that it would come installed in the vehicle. The product would be sold to the manufacturers at potentially higher volumes than with individual transportation companies. Our product also wouldn't require as much of a marketing budget as an aftermarket part might to be able to reach as many customers. Also, these aftermarket sensors like this one from TruckX are rely on Bluetooth and a cellular connection. Ours would be embedded vehicle telematics. It wouldn't be much more reliable. You wouldn't have to be constantly connected to your phone. It would notify you through the truck. It wouldn't notify you through your phone if the trailer door came open. So I think you'd be much more likely to notice. And so in feasibility, we're very confident that this product is feasible as somewhat similar systems already exist, and we have some diagrams and demonstrations later on to hopefully prove it. We're also confident that this is something the market wants, as there's a strong interest in vehicle telematics in the transportation industry. So according to transportdive.com, one video telematics provider saw a 63% increase in customers in 2020. So there's certainly a lot of potential here. And yeah, with that, we can go to the next slide.
So according to the Federal Motor Carrier Safety, there were approximately 4,998 large truck accidents, including buses as well, from 2019 to 2020. The reason for these accidents were quite many. So they span from perhaps unevenly distributed load and cargo, driver exhaustion / driver negligence, failing to lock the trailer doors, and much more. Our design would be able to reduce this accident by letting drivers know when these issues arise, so drivers are able to exercise good judgment in order to avoid accident, not only with their accident, but also accident with other individuals on the road. And with that, we go to the next slide.
Our design is essentially a adding to the CAN bus network with a magnet and proximity relay reed switch. A benefit of the system is that we are simply adding to existing CAN lines that are fed through the trailer system that already exists to be able to monitor tire pressure, and as well as being able to use the stop and turn signals. So we're not necessarily adding a new whole complex system. We're just adding to the pre-existing one. And our magnet and switch sensor would operate as a state machine. You would essentially go and check what condition the vehicle currently is. You would check if the vehicle is currently in park, if it's reversing, or if you're currently in drive and you're going over a set speed in which the system would need to alert the individual. It wouldn't really be necessary for when you're in park and you're just simply unloading. And the system would then take this communication and send it to the infotainment system so that the driver would be able to see that something is going on with the back hitch. And besides this, we'd also want to improve it by adding live data monitoring and being able to view the data at a later point. And this would be beneficial in other situations, such as when you're dealing with a semi-truck that needs to be refrigerated. You would obviously want to reduce the amount of time that your door is open because you're dealing with things that need to be cooled, and it's going to heat up pretty quick if you're opening your door too much. And you can go to the next slide.
All right.
I actually had an old Arduino kit that had a bunch of sensors in it. So it was actually pretty nice because I had a magnet sensor that operates similarly. So on the left, you can see the code that I created for the system. It saves the current state of what the vehicle is in. So if the vehicle door sensor is low and it switches to high, that means that the door is opened. And if it switches from high to low, that means that the door sensor is currently locked. On the right, you see how the door sensor would report to the infotainment system. It would be live monitoring, and then when it detects an open, it would then report to the infotainment system.
All right.
Switch to the next slide.
Yeah. Sorry. Oh yeah, expansion integration. Yeah, we think there's lots of potential here. So we think this product would fit in well with Modine's current line of electric vehicle products. You know, it's similar in the regard to these other products in the regard that it's sold to the manufacturer of the vehicle as an embedded solution. You know, comes installed in the vehicle, and we think there's a lot of opportunities for expansion here. This could be expanded into a line of products composed of sensors using vehicle telematics for mainly for transportation companies. Can move into more complicated things like sensors that are placed on the axles of a trailer to detect if the trailer is overloaded or the weight's unbalanced, like we mentioned earlier. Could even provide an opportunity for Modine to expand into other areas of vehicle telematics, like the collision notification system or fleet monitoring that collects data on the status of the entire vehicle. Like one example that would fit in well with Modine's thermal management solutions is products that monitor the temperature of the engines or the trailer itself. Like if it's refrigerated, and use telematics to record and report that data to customers. And yeah, like another advantage of this being like, yeah, the potential of this, like, yeah, it might be cheaper because like there's no annual fee. Like with the trailer X sensor that I mentioned earlier, the aftermarket one. So, and that might make it safer because, customers might be more likely to use it long term if they don't have to pay $50 a year. Or it could also be integrated into a monthly fee that the truck manufacturer might have. Well, yeah, the point is there's a lot that can be done with the combination of sensors and vehicle telematics, and we're excited to keep exploring those possibilities. And yeah, that's our presentation. Thank you. So, yeah, we can take questions now. Thanks,
Thank you for the claps, Ryan.
Yeah. Is that
Yeah, good job, guys. Darius, go ahead. Ask the question.
Yeah, this is really cool. I really like that you did the little demo with the Arduino too. Were you able to hook that up with any of your CAN bus code for Arduino and have it report that over CAN as well?
I didn't figure that out yet.
Okay.
I was I had not gotten it to fully work, but I had begun mixing the code together.
Okay.
And I'm sure it was like another half week until I would get it to work, but
Yeah, totally. If you did do that, what kind of messages would you send on CAN? Like what all would you include on the status message?
it would. So if we were looking just at the door sensor, we can obviously, we could track when and how the door opens, and then you can theoretically in the system, when the driver puts it or takes it out from park and starts moving in reverse or drive, we can then have the system request data of what the current status is of the door. So let's say you put in a drive, the system requests data, the data comes back, hey, the door is currently open, then we record it. But theoretically, we could do, if the sensor is going on and off, we can also, like if it's switching rapidly between closed and lock, that's another sign that your lock is malfunctioning or not, or like it's swinging open. So that would record not necessarily that the door is open, but that you have a sensor issue, and that you should realistically pull over and address it.
Okay, cool. I like the focus on telematics here. What made you decide to work on like a truck door switch? What inspired you to do that?
Well, we knew that Modine does a lot of commercial vehicle work. Obviously, it's a lot to do with battery systems, but we looked at what is like the largest issues that you can think of when you think of a semi truck, what type of accidents that you're dealing with. And there are a lot of cases where cargo is improperly loaded into the back and it causes weight shifts. There are a lot of times where the cargo door is open and there's spillage across the highway. So we try to think of systems that would reduce the high risk possibilities of accidents. Another idea that we had is a lot of the time you're dealing with truck drivers who doze off while driving. We thought of adding a camera sensor to track eye movement. And if it's showing that you're having low visibility of the road or you're not looking at the road enough, to send a message that says, hey, take a 10-minute break, pull over,
Yeah. Because we also thought, yeah, those are like the trailer sensors were the most unique of our ideas. And also, yeah, the door sensor is probably the most realistic that we could demonstrate right now. But yeah.
Yeah, it's pretty hard to demonstrate an axle sensor working
Right.
and showing weight distribution when we don't have a semi truck.
Yeah, this is a great project. Thank you. Thanks for the presentation too. Those are all the questions I have.
All right.
Sweet. I think we have time for one more question if anyone has it. Otherwise, we can start transitioning. Sweet. Well, nice job, Team 2. That was great. And I'm going to have to install one of those for my own trunk.
Yeah.
Ryan, I think
Hey.
Ryan, I think you need one that monitors when your car gets broken into
Right.
after number 3 for you. But that's a whole nother conversation.
That's a whole other conversation, right? Yeah. I need some sort of glass breaking sensor. All right, Team 3. We got
All right. Well, good morning for everyone in Central Time. For me, it's not really morning, but it seems like everyone else is just not in Ohio. So, I mean, good morning to you guys. Let me get this presentation popped up. I just want to make sure. Can you see this all right?
Yes, Stephen.
All righty. The rest of my team, are you ready?
Yep.
Yes. Sounds good. All right. This is our Modine manufacturing final presentation. Again, we're Team 3. My name's Stephen Bittner. I'll be followed up by my colleagues, Trey Vocon, Gavin Harwood, and Charles Farrell. So to start off our problem statement, I came up with this. So as the adoption of electric vehicles continue to surge, ensuring the safety and reliability of the CAN bus systems has become a critical challenge. The CAN bus serves as a backbone for interconnecting control units within the ECUs of a vehicle. And through our research through this internship promoting manufacturing, we have come up with an idea to solve some of the safety issues with these current EVs.
Yeah. So with that, how do we approach improving longevity and safety in battery units? So there's a lot of different ways that we can go about that. So like, for example, we can use CAN bus to gain advanced battery analytics. This will help with diagnosing different issues or maybe malfunctions within the battery, as well as even getting fleet statistics, advanced data on energy usage. This is really helpful for cost analysis. Those analytics may also help with doing preventative maintenance, which minimizes downtime for a fleet, both in semis and maybe in the construction field. Like especially in a construction environment, having downtime in any machinery is very costly, and we want to avoid that as much as possible. And in addition, like in EVs, charge times are long, even with level 3 fast chargers. A charge time can be like 30 minutes. So then, in addition to that, to kind of help with minimizing downtime, us as a team kind of felt that having swappable battery units or like interchangeable batteries, kind of like changing the batteries in an RC car, would be a very nice feature to have, or a nice feature to support. Other things that we can do to improve longevity are, taking a close look at charging and discharging behavior, optimizing that field. A lot of wear happens on a battery when you charge and discharge it. And then make sure that we're doing proper thermoregulation is very crucial to that as well. Some other things to improve safety would be adding fire suppression. And then there's other resilience stuff that we can do in a CAN network, such as following J1939 and making sure that we're doing all the proper stuff to our CAN network to make sure it's resilient to outside interference. So yeah, so kind of a bit more story on a lithium-ion cell. So temperature and cycle life. So the temperature of the operating temperature of a lithium-ion battery is very important. It's important that it gets maintained. So battery capacity fluctuates with the age and the temperature of the cell. As you can see by the chart on the right, that lower operating temp, mitigates cell deterioration, but it comes at the cost of capacity by up to around 15 to 10%. But a higher operating temperature, the cell deteriorates quicker, but you have an increase in capacity. So temperature regulation in this sense is very crucial. And, using a CAN network to add operator and software monitoring could be very useful telematics to have for a semi-driver or the operator of any EV vehicle. As far as the thermal regulation goes in battery cells, Modine has largely solved this.
So I was in charge of figuring out fire safety and fire suppression. So first we want to start off with what makes lithium fires so dangerous. And that's because they produce their own oxygen, which makes it very difficult to extinguish it. With this being said, I found a few areas of fire suppression. Some of these can't be done within a vehicle. Some of them have to be done outside. But the first one we did was Rosenbauer's. It's their best device, best standing for battery extinguishing system technology. Essentially, it's a spike system that will go under the car. It will shoot up a spike and spray water into the battery. It's about 100 PSI, and it goes for about 10 plus minutes until the fire department or whoever decides that, hey, this is no longer a problem. The second one I researched was called the Cold Cut. It's a Swedish system. It's a cutting extinguisher. So if you could think about it, it's almost like a really high-powered pressure washer that will not only put out the fire, but cut through it. This uses about 58 liters a minute, which seems like a lot, but the time it takes to cut through this battery and cut through the water is a lot faster than any of the other options we have now. We also have just normal CO2 foam extinguishers. I mean, everyone has fire extinguishers. They're from houses to cars to everywhere. Even the ambulances I drive every day have a fire extinguisher. The problem with this being is that you're so close to this lithium fire, and who knows what could happen when you're at this range. We also studied some powdered fire suppressants. So you can use powdered graphite, you could use dry chemicals, or you could use some sort of sodium carbonate. In my research, I found that having a system inside of the truck that would at least spray some sort of foam or something to keep the fire suppressed until some sort of fire department could get there was the best way we had.
Yeah. So then, we kind of get into charging and discharging behavior. A lot of wear happens onto a battery during this period when electrons are moving through the cell. The cell degrades just naturally through a chemical process, but we can optimize and manage our charging and discharging behavior to help manage this a lot better. So I guess into fast charging. One of the fastest charging setups that you can do is level 3 charging, level 3 DC charging. Modern studies show that this has very little effect on cell lifespan, contrary to kind of the rumors. But what really does do a lot of damage is charging to a higher voltage or capacity. In the graph on the top right, this shows this, how different cell voltages over a range of cycles ultimately affect the capacity of the cell. So this is why you may have heard the term, or may have heard something, that you don't want to charge your phone to 100%, instead charge it to about 80%. Well, this comes in because the nature of the cell is that the higher voltage you charge it to, the more it degrades. Leaving batteries fully charged, data shows that this has minimal effect despite some of the rumors. The chart on the bottom right shows that. The one outlier that we see, the circle dotted line at the top, that is fully charging a battery and then immediately using it after. However, if you let it trickle charge or float charge, it has minimal effects on the battery along a wider range of time. So this kind of suggests that float charging or yeah, float charging or just leaving a battery sit after it's fully charged has minimal effect on that lifespan. And this kind of comes into our swappable batteries. You know, how do we approach charging a battery? How do we approach managing it? How do we approach discharging it? Now the level 3 chargers are still kind of slow, but you know, if you're creating a battery unit in an industrial setting, like for example, a hybrid unit on an excavator, right, for maybe city construction, having a swappable battery is, you know, crucial in that kind of circumstance. So yeah.
Yeah, so after researching general battery maintenance and fire safety, we came up with the schematic on the left. So you can see individual nodes have a fire suppression nozzle, a battery unit, and a BMS unit. And we would have a private CAN bus run throughout this entire kind of system. We would have a BTMS master controller kind of orchestrating everything, as well as hooked up to the rest of the EV to power the car, and as well as connected to the EV public CAN bus to make sure messages are still kind of being sent elsewhere to the car. We would also have a separate microcontroller linked to the BTMS master controller through CAN bus. And that would also be connected to the dashboard to relate important diagnostics and information to the user. On the right, you can see a real world example of this. That is the Tesla battery, and you can see the different nodes kind of stacked on top of each other. We would take this and kind of modify it slightly. So beyond that, for our hardware and software layout, individual nodes include, like I said, a battery unit, a BMS unit to manage that battery, as well as a fire suppression nozzle. These battery units are swappable, so this would improve overall fixability and maintenance, and it would also minimize downtime while fixing these nodes. A master BTMS helps control these individual nodes, and it helps kind of monitor the system and ensure that there are no errors or fires happening in the battery system. So we would have a private CAN bus for instant and robust system-wide communication. This would be between nodes and the master BTMS controller. A microcontroller would be separate, but would be wired to the master BTMS. It would store all data, and it would also write and request data through the BTMS. This would be used for projection to the user dashboard, real-time diagnostics. So that includes a real-time range for the user, as well as simply just ensuring that there are no errors happening. This would also provide an extra fail-safe in case the BTMS misses trends in the data. So that would include a rising temperature or a very rapidly decreasing temperature. And this would serve the need of emergency fire suppression or shutdown of either individual nodes or the overall system. And BTMS data that's being wired to the microcontroller would include current battery system and sensor information. So that would be kilowatts per hour output of the EV, internal, external temperature, overall energy capacity, as well as individual node and sensor IDs. And beyond this, we also created a pseudocode layout. So we'd first define all the pins on the microcontroller, as well as define all the BMS libraries and or connect pre-existing firmware to the BTMS and BMS. We'd use a variety of different loops and if statements to help filter out CAN bus messages, as well as send those messages. That'd be between the BMS units and nodes, the BTMS, as well as the microcontroller. We would also have loops for the microcontroller to write data to the dashboard for display. This data would include system status and a real-time range. We would also have separate kind of filtering if statements for individual error handling and exceptions to ensure that error messages that are being sent between different nodes, if that happens, specify the certain sensor and or node. The BTMS would interpret this and either be notified by the microcontroller or it would take action by itself.
You guys can hear me, right? Okay, cool. So here is a theoretical loop of code for what the BMS to CAN bus communication will look like. I'm not going to spend too long on this. I'm just going to kind of skim through it and explain to you guys what's going on. So firstly, we set the sensor data, which will be connected to our microcontroller, those being analog read and analog read A0 and A1, where A0 represents a voltage sensor and A1 represents a current sensor. After that, we have to save the data into a CAN frame to then send it to the CAN bus transceiver. So firstly, we just create a CAN bus object. And then after that, we set the CAN bus ID and link. Note, these are arbitrary, but for our 6 different BMS units, we need to have a different ID for all 6 of the units. Sorry about that. For the mem copy function, this is essentially just copying the data from the 2 sensors. And what this method does is that the first parameter defines the destination location, the second parameter defines the source location, and the third parameter is just the size of the overall data. After this, we send the CAN frame to the CAN bus using a CAN write function. We're doing the first BMS and CAN CAN bus system. So my CAN 1.write is just sending data to the first CAN bus. After data is sent to the first CAN bus, we then print out a message to the receiver monitor saying that CAN bus 1 has received data. So what are the overall benefits and improvements of the system? Using a optimized BTMS system can greatly extend our battery's life. So what that means is basically controlling each individual BMS and battery unit. So one battery might need to be cooled, while the other might need to be heated. This comes at like a cost. So the first cost being the range of our telematic system, it is reduced. A pro of this system is that the durability and overall reliability of our battery system would increase. Using a modular battery design offers us with redundancy, and all this means is that we have a backup battery in case one malfunctions. We can also exchange dead batteries for charged ones. Using a modular design also introduces a more efficient heat dissipation as opposed to single battery cells and battery packs. And using the CAN bus linked to our BMS units, we can gather data and helpful statistics, which is pretty much invaluable to both maintenance and debugging. Using the fire suppression system, the spread of fires that happen to the battery system basically improves the driver safety and prevents them from spreading to the entirety of the car as well as the surrounding environment. So how can this help Modine? Using the CAN bus to identify isolated problems within each singular battery module, maintenance becomes simpler and the battery's overall efficiency can be improved. So increasing or reducing the energy supply to the entire system to make a more efficient system. Using the data gathered from the CAN bus, Modine could compile 2 separate reports, those being a driver performance report and the electric vehicle safety report. Using these 2 reports, they could then compare their electric vehicle models with competition, and based off of these 2 reports, they could then modify either the external electric vehicle itself or the internal battery system to overall improve the safety and performance of their electric vehicles. Thank you. Any questions?
Sweet, awesome, guys. Good job. We have time for like one question, and then we can move over to team 1.
Okay, yeah, my one question is, what gave you the idea for integrated fire suppression in the battery? I think that's a really cool idea.
Here, I can cover that. So when we were trying to decide on what we wanted to do, we had a few objects, and Trey came up with the idea of doing some research on fire suppression, which, working in an ambulance every day, my second job over the summer, we have a lot of issues with fires going on. I don't mostly cover those, but I mean, driver safety is a big thing, safety in general. I don't like taking patients. Other people don't like taking patients in any sort of critical care, and trying to find a way that helps suppress a fire, to help with environmental regulations, and help just with the safety of truck drivers and even just school bus drivers or any EV that we're going to be using is very hard to do. And it's something that not a lot of companies have previously done their model. So we thought that it would be a good twist to try to add something like that in there to at least suppress a fire instead of getting rid of it completely. At least give a driver or the surrounding people and environment some time to wait on for a fire department.
Yeah. Yeah, extinguishing a lithium fire is extremely difficult, but there are things that you can do to suppress it. The reason why I kind of had this idea is I think this last weekend here, I was going through the news and I saw something that a Tesla had caught on fire on the highway and caused a bunch of traffic. I was kind of thinking that, well, there has to be something that we can do. But, after searching around on my own time on the market, this fire suppression isn't really something that exists in an EV market. There is on an industrial power bank scale, but not really something that's been implemented into EVs. So we kind of thought that implementing that into our design would be something, massive that we could do to improve safety.
All right, thank you.
All right, great job, guys. I'll hand it over to team 1. You guys got about 20 minutes, so again, try and hit that 15-minute mark so that we have time at the end for questions. But get your surveys in, and team 1, floor is yours.
Okay, I'll go ahead and share my screen now. Can you guys hear me okay?
Yep.
Okay. Okay, so first I would like to say thank you to the Internship on Demand team, as well as the Modine team, for taking the time to witness our final program presentation today, and for also giving us the opportunity to work on this great program. My name is Samuel Oladeji, and I am a senior student at the Minnesota State University, Mankato. I am majoring in automotive engineering technology, and I'm expected to graduate in December 2024. Here with me, I have...
Everyone, my name is Ivaniko Sokumar, and I'm studying at the University of Pennsylvania. I'm majoring in mechanical engineering, and I'm expected to graduate in 2026.
And my name is Adam Holmes. I'm a mechanical engineering student at the University of Iowa, and I have a planned graduation for May 2025.
Okay. So coming up from our mid presentation, we talked about how the world is transitioning from the traditional internal combustion engine vehicles to the electric vehicles. And the 3 main components of the electric vehicles that differentiate them from the internal combustion engine vehicles are the motors, the batteries, and then the power electronics. These systems get hot during operation, and that is why they need to be thermally managed. And this is why this program was based on the understanding of thermal management in electric vehicles. And now we know that thermal management system cannot function properly without the use of a controller area network communication protocol. And that is why further in this program, we developed and learned about the controller area network, and then we look for ways on how to make it function into more use case aside the thermal management to develop a CAN scanner for a real-world EV application.
So this presentation, we will first cover basically the progress that we made since our mid-internship presentation. And one of the main progress points we've made since then is adding a 3rd transceiver to our originally 2 transceiver CAN bus prototype. We also updated the KeyCAD schematic. And moving on to the second part of this presentation, we'll be sort of going into our own independent product development and product research phase. The first step in this was the actual research of our market and needs for a CAN bus system. And we finally settled on basically a train operation and railway accident prevention system using the CAN bus.
So as Ivanico previously mentioned, before we got into the product research and figuring out a real world application for a CAN system, we wanted to go back and update our prototype and add that third transceiver. And as you can see, we also updated the KeyCAD schematic and added traces to the front and back of the PCB, which will just make maintenance and assembly easier. And it continues our robust design. So after we updated our prototype, we then went to the market research stage. And while we were looking into EV markets, we wanted to find something that was more unique than automobiles and trucks. And that's when we discovered the train market. And there already are existing systems for monitoring train safety, which we'll talk a bit about later. But the main use case for these systems is monitoring safety hazards and preventing accidents. And this market, the electric train market, is rapidly expanding. Europe has a decarbonization plan that they're trying to achieve by 2050. And both China and India are both on track to develop high-speed rails and have rapid electrification movements. Some of the safety hazards that are encountered are collisions and derailments. So this is a problem that needs to be addressed. Modine can provide for this application because of their background in thermal management. And also with their global presence, this is a global market application. So we thought they would be a good use case for this project. So
coming up from what Adam said, in the first quarter of the US, there was a record of 1,400 train accidents, and 66% of those train accidents were coming from derailment. And 14% of those 66% were caused by track issues, and some were caused by the drivers overspeeding, and the other were caused by head-on collision. So to then solve this problem, we went on to make research to see if there are currently an existing safety system embedded in the train that mitigates this risk and accidents from happening. And then we discovered the PTC, which is the Positive Train Control System. So the way the PTC works is that there are sensors on the tracks as well as stations around each tracks, and there's a GPS system embedded on the train. So the train communicates with the sensors on the track as well as the stations using the satellite communication. So it's like a remote communication. So basically how this PTC works is that whenever the stations, which are usually controlled by humans, whenever the station dictate that maybe the train is approaching a bend and it sees that the driver is going at a really high speed that would not make it successfully navigate that bend, it sends a signal to the driver at the monitor, telling the driver that, hey, there is a bend ahead, and telling him to slow down to a particular amount of speed to successfully make that turn. So if the driver does not respond to that promptly, then there's a circuit breaker embedded in the train that the people at the train control station can initiate and then cause the train to stop or slow it down. But we realized that there's an issue with this communication signal protocol because each countries and zones have their own different signals they use to communicate, which sometimes if a train from another zone is going to another zone, might have a communication issue. To solve this problem, we came up with our CAN bus safety system. And the CAN bus safety system is going to be a self-sufficient system that would not need any external interference, but it can independently make judgment. To make this system robust and functional enough, we decided to come up with a drivetrain control module, the body control module, the wheel condition monitor, the brake control module, the system control module, the battery management system, the track condition monitor, as well as the motor controller ECUs. So all of these ECUs communicate with each other to make the train safe and function better.
So going from that high level approach, we can actually take a closer look at how each of these ECUs would be functioning. So on the left side, I have basically like a breakdown of one of those ECUs. And in this case, we'll take a sensor example. So first, the multiple sensors on the train and along the cars would feed into what's called a shift register. Specifically, we found out using a parallel in serial out shift register would probably be the best use in this case, so that we can basically compress all of the sensor data into one pin for the microcontroller to use. And the microcontroller can then process that information or directly send it through the CAN bus network as a data frame and signal to other different modules within the system, whether or not there are any errors or irregularities detected. On the right side, we have a CAN controller module. So rather than actually getting information from sensors or some kind of external input, this microcontroller will receive information from the CAN bus itself and basically from other modules. And based on that information or other data frames passed in, it will make a decision and pass it to the different controllers. So an example of this could be detecting wheel conditions and then applying a change in the motor controller.
So while designing our CAN bus safety system, we considered and we kept in mind the current standards that are applicable in that market. So one of them is the ISO 22163. So that deals with the quality management system. So that is usually what standardizes and monitors the quality of safety systems, fail-safe systems in the train industry as well as automobile industry. We have the ISO 269. It's basically a standard, for design and manufacturing processes to ensure that it is safe as possible. And then we also have the ISO 45001. Is the occupational health and safety management system. So this just ensures that all of these systems are safe for engineers and other humans that will be coming across them to operate with it without any hazardous issue.
One of the first challenges that we encountered through the second part of this project was finding relevant and reliable information. Integrating CAN systems into trains is not nearly as common as on other EVs. And our research kept coming back to those accidents and railway safety hazards. And so to solve this, we took a bottom-up approach where we found the issue and then we worked back towards the solutions and how to integrate those into the CAN system. Another challenge we had to overcome was making our design unique from existing communication systems. And a lot of the existing systems monitor the tracks themselves and the sensors are on the tracks. And we've come up with some unique solutions to monitor things from the train itself. So monitoring friction on the tracks, making sure things are properly lubricated, monitoring the temperature of the tracks in different weather conditions, which all work together. All that data can be collected and then proper actions can be taken. There are a couple of drawbacks of the CAN system, which we still have yet to figure out. And one of those is the security. The CAN system is less secure than existing systems and the scale. Trains have a lot of sensors, even more than a car does. And Wi-Fi and Bluetooth can help with some of those issues, but integrating it is very challenging.
So we developed a preliminary bill of materials for one prototype of our CAN system. And basically in the top two rows, you can see that we have two different types of microcontrollers. The first is an Arduino Uno, and the second is Arduino Mega. And the reason we went with two different ones is mainly because of the sort of the variation in ECU needs that we have. So generally, most of the controller units will need lesser pins, so the Arduino Uno would be sufficient for those purposes. But for the more sensing related modules, those would need a lot more pins just to take in more input. for larger train car systems. So the rest of the components are pretty standard and were similar to what we came up with last time. The PCB, transceiver, resistor, capacitor, and additionally this time we have the shift register, which again helps sort of compress that data. We decided not to include the sensors in this case just because it would vary greatly from train to train, since the car amount per train varies a lot, and sometimes these trains also come fitted with sensors already, as Samuel mentioned earlier, because of the PTC system that exists in some of them. And at the end, we came up to a total of $362 with a theoretical start build date of August 29th.
So peradventure, this program was still continuing. Our next step will be to design a schematic that includes the new microcontrollers using the Arduino Uno and then the Arduino Mega 2560, and then develop a working prototype that can be integrated into the train for safety. And that'll be the end of our presentation. At this time, would like to welcome questions if there be any. Thank you.
Awesome job, guys. Choo choo.
Yeah, nice work on this. So you did have a bit of a slide on this earlier, but what attracted you to the rail industry for this?
I can answer that. So we decided, like we said initially, we noticed that there have been a lot of accident in the rail market so far, and there has not been any much safety protocols, or should I say safety steps, that have been taken to mitigate this risk. For example, now the train tracks, there's usually very poor maintenance on the train tracks. And in terms of like derailment, there are usually a lot of issues with derailment. For example, we can see the accident that happened in India recently that was caused by derailment. And so far, so good. The PTC is not really doing a good job in solving that problems because there are always communication issues in different regions, and that usually causes the train not to receive, signals and notifications of maybe an possible dangerous, situation ahead, and this oftentimes lead to accident. So we decided to focus on the train market because the world is evolving and is going into much more robust transportation means. And we see train as one method that will be largely used in the future. So that's why we chose that.
And to add to that, the train market is not there. There's not a lot of other competitors right now as far as CAN bus implementation. So we saw it as an opportunity to be one of the first ones to integrate it.
Okay, cool. Good points there. We actually have some battery thermal management systems on battery-powered electric trains in India right now. So this would be a fun addition to those.
Great, great.
I'm curious for you guys, and great job on the presentation. You talked about your prototype, and maybe I missed it, but is there something specific that based on that bill of materials and based on the working prototype that you would be, I guess, what is the hypothesis? What are you trying to solve? What is the reason for building that prototype?
So the prototype basically was to ensure safety systems to ensure safety in the train. So like we talked about the PTC initially, the PTC does the job of like sensing, for example, now in a train track, right? If another train is coming, so the PTC control station will signal the train driver that, hey, there's another train coming. And the driver can make adjustment as needed to accommodate both of them to use that location without any issue. Or for example, let's say there's a head-on collision ahead. Maybe there's something we call the cross-by trespassers. So we know that there are some sections on the road where you have this cross signs that deprives cars from passing when trains are coming through. So the PTC does a job of like sensing that and telling the driver ahead that there is people crossing, but apparently the PTC cannot prevent those issues. At least from our research, we did not see anywhere that it can sense like maybe a passerby coming and cars coming, and then it stops the train ahead of time. No, most times it still run the train over. It still run the people over, sorry. So this our CAN bus safety system will be equipped with sensors that can read the track condition. So peradventure, if the track is cracked somewhere or if the track is bad somewhere, the sensors are capable of sensing these things, of reading, of conveying this information to the driver and to the train system 15 kilometers ahead. Now, from our research, it takes a train that is going as fast as 160 miles per hour to come to a complete stop in a span of 3,000 meters. So our sensors are able to even make this correction as far ahead as 15,000 kilometers before it approaches this danger zone. And so the CAN bus system can easily communicate to other modules like the motor controllers, the brake system to stop the train, just so that, hey, this is not safe, you got to stop. And then it's going to stop the train. So basically, just to avoid these issues as much as possible. Like we said initially, some of the cause of derailment was because of, one wheel bearing and rounded wheels that then could cause the wheel to pop out, during operations. Now, our wheel condition monitor will be equipped with sensors that will be studying the conditions of the wheel every time. Should in case the wheel is portraying some kind of abnormal behavior, it's going to communicate with the system that, okay, this wheel doesn't seem to be okay. And that will come off to the driver's dashboard, telling him that this wheel needs maintenance. And that can be changed before it leads to any accident. And so for speed as well, too, it can sense if the track ahead is maybe bent or crooked, and that will tell the driver to slow down, or if the driver doesn't respond on time, it will automatically kicks in by stopping the train by itself or maybe slowing the train.
Awesome. Keegan had to jump. We have another presentation at the top of the hour, but yeah, I'll leave it there. Team one, excellent job. Very unique market, especially for Modine. I didn't even know Modine was into trains as well, but I think that was good. Everyone else, make sure you get those surveys in and submit it so that we can give that feedback back to you guys, so you can kind of see where you're improving and still some things that you need to work on. But with that being said, that's the end of the program. You guys did a fantastic job. Probably, I mean, our most successful program yet. So it's awesome to see you guys really giving it your A++ effort. So I appreciate it there. Darius, thank you for being here and providing feedback, good questions. But yeah, as far as kind of next steps go, we'll be sharing that feedback just from both presentations. Certificate of completion, you can kind of use that to post on LinkedIn. Alumni details, and then we'll be talking with Darius on kind of just like some of the Modine job application stuff, next steps, and then getting your second rounds of payment here soon. And then just a reminder for you guys, just if you haven't already, connect with Keegan and I on LinkedIn. We can, give you any sort of help, or if you want to browse our connections, we can connect you with someone in our network, complete your exit surveys. And then, yeah, don't be afraid to post this pre-internship on your LinkedIn, add it to your resume. I can help out with the language of that if you need. But yeah, Keegan and I will always be here for you guys to help out. So I appreciate the program and wish you guys the best of luck in your fall semester.